So we're going to move on to section 10.3, and we're going to do more trig functions. And basically we're going to build on what we've already seen about sine and cosine. Problems are 1, 3, 5, 21, 23, 45, 67, and 71. Again, a lot of exercises, but hopefully most of them will go pretty quickly. So the new functions we're going to see are tangent, cotangent, secant, and cosecant. We're also going to learn some basic trig IDs. So identities are just true statements. And we're going to see some basic trig values. I guess I'll put in values. I'm going to ask that you work through examples 1, 3, and 4 from the book. Okay, so I'm going to start out defining some things that you've seen before, and then I'm going to move forward. So given a right triangle with acute angle theta, we have, and I'm going to just sort of draw a diagram here of my right triangle with, actually let's make it a little bit bigger so we can have a nice fun picture. So apparently I don't know how to draw triangles. That's a thing. I'm just having a rough time. Okay, here's theta. There's my right angle. So I've got my adjacent side. I've got my opposite side. Right? And then I've got my hypotenuse. So we've already seen sine theta is opposite over hypotenuse. We've seen cosine theta is adjacent over hypotenuse. There's a new one. We're going to call it tangent theta. So tan theta is opposite over adjacent. All right. Now that's 3 trig functions, and so that checks off this new one. We've got 3 more, and the way it works is that each one of these has a sort of friend function. That's the multiplicative inverse. So not the inverse function, but the multiplicative inverse. So the multiplicative inverse of sine is cosecant. So cosecant theta is the hypotenuse over the opposite. The multiplicative inverse of cosine is secant theta. Having a hard time just drawing things in general today. And this is going to be the hypotenuse over the adjacent. And finally we've got cotangent theta, which is going to be the adjacent over the opposite. Now, because we know what sine and cosine are for the special angles, we can figure out what secant and cosecant are because it's just 1 over those. I do want to take a moment and say, sine is 1 over cosecant, and cosine is 1 over secant. So sometimes people mix those up. I don't remember why they're named this way. I read about it once, and it made sense at some point in time to someone. I'll say that. All right, so we've got theta, and I'm going to give you in degrees, and then theta in radians. And then we're going to see sine theta. We're going to see cosine theta. And we're going to see tangent theta. And then we're going to move on to cosecant theta, secant theta, and finally cotangent theta. We've got 0 degrees, 30 degrees, whoa, 45 degrees, 60 degrees, and finally 90 degrees. And then converting these to radians, we got 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. So remembering from last time, this is going to be 0, 1/2, root 2 over 2, root 3 over 2, and 1. And, because it's root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and finally root 4 over 2. And then we get the exact same pattern but backwards, 0, 1/2, root 2 over 2, root 3 over 2, and 1. And now, so let's explore this row for a minute. Oh dear, that was unfortunate. Don't know why that happened. Let's explore this row for a minute. So if I'm looking at tangent that's opposite over adjacent, I claim that's the same as sine over cosine. So I'm just going to write this out here. We'll look at this more later, but let me write sine theta over cosine theta. And sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And now let me multiply this by a useful form of 1, that is hypotenuse over hypotenuse. And I can cancel there and there, I can cancel here and here, and I get opposite over adjacent, which is exactly tangent of theta. All right? I'll rederive this another time, but basically that is to say that tangent is sine over cosine. Okay, so if tangent is sine over cosine, we've got 0 divided by 1, and that is 0. Then we've got 1/2 divided by root 3 over 2, which is 1 over root 3. We've got root 2 over 2 divided by root 2 over 2, which is going to be 1. We've got root 3 over 2 divided by 1/2, and that's root 3. And finally, we've got 1 divided by 0. Well, we can't divide by 0, so we just say undefined. Now we notice this relationship that if sine of theta is opposite over hypotenuse, cosecant of theta is exactly 1 over that, right? It's the multiplicative inverse. So to complete the rest of this chart, I just do 1 over the corresponding of the 3 columns. So 1 over 0, again, here we have undefined. That's 1 over 0. Now 1 over 1/2, that's 2. Then 1 over root 2 over 2, well, that's going to be 2 over root 2. Let's just say this. This is going to be 2 over root 2, which is root 2 times root 2 over root 2. Cancel these, and we're left with root 2. So this is just square root of 2. We've got 1 over this, which is going to be 2 divided by root 3. And finally, 1 over 1, which is just 1. Now, 1 over cosecant is sine. 1 over sine is cosecant. But if sine was this pattern in this direction, then cosine is that pattern in that direction. It's the same pattern, so 1 over that pattern is going to be the same pattern. So again, we've got undefined, 2, root 2, 2 divided by root 3, and 1. Let's make that 1 nice and pretty. And 1 over tangent is cotangent, so 1 over 0, undefined. 1 over root 3 is root 3. 1 over 1 is 1. 1 over root 3 is 1 over root 3. And this 1 over undefined, we can't really do that. But if tangent was sine over cosine, 1 over that's going to be cosine over sine, right? It's going to be the same thing but flipped. So cosine over sine, that's 0 divided by 1. Oh, this means we've got 0 here. And that is the whole chart for our special values. So let's use these special values a little bit and answer a question. So example, given a right triangle with an angle of 60 degrees, next, oh dear, I scrolled up instead of down. There we go. Next to a yeah, I seem to have something wrong here. Let me just finish this next to a side of length 10 feet. What is the length of the opposite side? So we could have done this in the last section with sine and cosine, but it would have taken a little bit more work. We would have had to compute the sine, then the cosine, and then somehow work those together, or mess with a number of different ratios. But now this is going to save us a step because we can just work with tangent. So solution, we know that tangent of theta is equal to the opposite over the adjacent. So we just need to do tangent of 60 degrees. I'm leaving a space. I'm going to write tangent of 60 degrees is going to be, well, two things. The tangent of 60 degrees, we've calculated it right here. It's square root 3. And it's also opposite over adjacent. So the adjacent is 10 feet, and the opposite is what we're looking for, right? Well, this just tells us that the length of that opposite side is 10 root 3. 10 root 3 feet. Okay, that's the answer. So that was pretty quick. Let's do some major trig identities. And so what constitutes a major trig identity might be a little subjective, right? So I'm going to give you trig identity number 1, which we've already talked about, and that is that tangent theta equals sine theta over cosine theta. All right, we've already seen that one. That was what we sort of sketched a proof of here. I mean, actually, it's a fairly complete proof. And we use that to help us fill out this part of the chart. To fill out this part of the chart. But that's just, using the definitions in this row here. All right. The next one is that sine squared theta plus cosine squared theta equals 1. And I'm going to add a little note here. So note sine squared theta, this is weird notation, but this means sine theta squared. Also, this is called the Pythagorean identity. So it's essentially an application of the Pythagorean theorem. And why is that? Well, I'll derive it pretty quickly for you. But first I want to write down major identities 3 and 4, and I think they are way less major than identities 1 and 2, but this is how the book has it listed. So tangent squared theta plus 1 equals secant squared theta. And major identity number 4 is that 1 plus cotangent squared theta equals cosecant squared theta. You do need to know these. But basically, if you know this one and you know this one, you can derive the others pretty quickly. And honestly, you can derive 1 and 2 pretty quickly as well. Oops, didn't get that. Okay, so number 1 just followed by the definition of sine and cosine and tangent, with the opposite over the adjacent coming from opposite over hypotenuse divided by adjacent over hypotenuse. So now let's look at number 2. What I'm going to do is I'm going to look at, any point on the unit circle. Okay, and that point on the unit circle is going to correspond to, so let's look at this point. It's going to correspond to some angle theta, right? And the coordinates of this point are cosine theta, sine theta. And this is true for any point on the unit circle. It's the sine and cosine of some angle. And what do we notice? This is a unit circle, and this is a radius, so this length right here is 1. Well, what's the distance? This shape is just this is a really unfortunate place to put my my very important point on. Let's make this at least a little bit rounder. Okay. Well, this distance here is 1. And what is that? Well, that's exactly cosine theta and sine theta, right? What's happening? If I compute the distance from the origin to here, to cosine theta, sine theta, well, what's that distance? Well, on the one hand, I know it's 1 because it's a point on the unit circle. But let's use the distance formula to figure it out. So 1, which is the distance, is going to equal what? The square root of, well, it's the difference between cosine theta and 0, because we're going to look at the difference of x coordinates. So cosine theta minus 0, quantity squared, plus, so that's this difference, plus now the difference in y coordinates is going to be sine theta minus 0, quantity squared, and we take a square root. Well, if I square both sides and I simplify the fact that I'm subtracting 0, what I get is precisely 1 equals cosine theta, quantity squared, plus sine theta, quantity squared. And remember I said there's this notation, the way we write sine theta quantity squared is sine squared theta. It's sort of unfortunate notation, but this is how we do things with trig functions, because we have to square them so often. So what we got was, just by looking at the Pythagorean theorem, or the diagonal line theorem, or the diagonal side of a triangle theorem, or however you want to call it, we get exactly sine squared plus cosine squared equals 1. Now, how do I get 3 and 4? Well, 3, it follows from, I take sine squared plus cosine squared, and I'm writing the equal sign a little low, you notice, and I'm going to divide both sides by cosine squared theta, and what does this become? Well, sine squared over cosine squared is tangent squared theta, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared theta. And number 4 is going to follow the same way. All right, I'm gonna start with sine squared theta plus cosine squared theta equals 1, but now I'm going to divide both sides by sine squared theta. And if I write down the definitions of these, well, I've got sine squared over sine squared is 1, cosine squared over sine squared, that's going to be cotangent squared, and 1 over sine squared is going to be cosecant squared theta. So that's how we prove part 4. Now, what I'd like for you to do is watch the following, which is I'm going to ask you to prove a new identity using those identities. So prove that tangent theta divided by cotangent theta is equal to secant squared theta minus sine squared theta minus cosine squared theta. Now, at first, this can look pretty daunting, but what I want to convince you to do is to go through a number of these, and then you'll start to see what works when. So I'm going to give you a second to just look at this and see what you can do. So what I'm going to do, and what is often profitable, is I'm going to start with the left-hand side. So left-hand side. The left-hand side is tangent theta over cotangent theta. And I'm going to write out what each of these are. Well, tangent theta is sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. Yeah? Well, now if I simplify this, this is a fraction upstairs, this is a fraction downstairs. What do you do with a fraction of a fraction? Well, the top part stays where it is, and the bottom part goes to the other side. So this becomes, this cosine is going to go down here, and this sine is going to go up there. That's what's going to happen. So I've got sine squared theta over cosine squared theta. Yeah? Now, what is sine squared over cosine squared? Well, that happens to be tangent squared theta. Okay? So this is tangent squared theta, and and this is by identity number 1, right? Sine over cosine is tangent. Now by identity number 2, tangent squared theta is equal to secant squared theta minus 1, right? Identity number 3, that's this one. Now what I've actually got is tangent plus 1 is secant, or tangent squared plus 1 is secant squared. But what I can do is subtract 1 from both sides of this, and I'll get tangent squared theta is equal to secant squared theta minus 1. And that's what I'm going to do. So by identity number 3, tangent squared theta is secant squared theta minus 1. And finally, by identity number 2, I'm going to rewrite this 1 as sine squared plus cosine squared. Now, you might say, but those are subtracted, but that's because this is a minus 1. So if sine squared plus cosine squared is plus 1, then minus 1 is going to be minus sine squared minus cosine squared, right? So this is going to be secant squared theta minus sine squared theta minus cosine squared theta, and that is exactly the right-hand side. So we're done, right? I just showed that this side is the same as this side, step by step. Okay? Now I would recommend looking for a few things here. So this is a general strategy that I normally follow. So first step, I put things in terms of sine theta and cosine theta, because I can write every single trig function. So remember we started with sine and cosine. If we look at this chart, I can write everything in terms of sines and cosines. Okay, it might not be the most efficient way, but probably if you push things around, you can write things in terms of sines and cosines, and then you can apply some other rules. So that's my first thing that I do. My second thing that I do is I try to apply the Pythagorean identity. That is that sine squared theta plus cosine squared theta equals 1. And when I say that I'm trying to apply the Pythagorean identity, I mean either this one or this one or this one. But if I've put everything in terms of sines and cosine, I'm mainly looking for this one. Now, the third thing that we're going to probably end up doing is simplifying, which it tends to be adding and subtracting fractions. All right, that's what it often ends up being. So as you approach these identities, I'm going to say it's probably worth going through a fair number of these and going through the examples in the book to try to see how we're applying these different identities. But you're basically going to be using these major trig identities and manipulating the trig functions. At first it's a little daunting, but if you just keep going through it and keep at it, you'll eventually start to see patterns. All right?